Okay, welcome to my webinar. Today I'm going to be talking about how to prepare or make specifications when ordering piezo ceramic elements because we have certain requirements that we need in terms of performance and for our application. So I'm going to be discussing how do you arrive at those properties. I'm not going to talk about how do you measure how the properties are measured, but rather once you're kind of farther along in the process, you have, let's say, working prototypes. Now, what is the proper way to look at it? Because if you don't, I guess, look at the process properly or what you're really going to get from your vendor when you give specifications, um, you may not be prepared or you may not have reasonable expectations. So let's continue. I'm going to give an outline first, usually. So I'm going to talk about the general view of tolerances with regards to piezoelectric elements, and they're also called, chips, crystals, transducers, and the assembly as well, about how you. Well, actually, we're mostly going to be talking about the elements themselves today, which then will go into your assembly, which that is typically your final device. Although some devices do mostly just focus on the element itself. Um, I'll talk about what can we specify, which is basically the electrical and mechanical parameters, and also the methodology for determining specifications. Um, so it may be different than what you are used to in other applications. So typically we're very used to specifications like for mechanicals, the size of like mechanical parts. Like I wanted 35 point, you know, 35 millimeters plus or minus 0.1 millimeter, or we have different dimensions we do. That's a common area where tolerances are given. Also in measurement devices, there are tolerances, and we usually have calibrations associated with those. Note that for piezo elements, there's not like a calibration factor that the manufacturer puts in. So we need to be very realistic in terms of, are we helping the process or are we hurting ourselves by thinking we have something better than we do? So we're going to talk about the methodology for determining specifications, step-by-step kind of approach, and true ceramic vendor stories. Yeah, it sounds exciting. And I'm not going to talk about which companies there were, which vendors they are. This is kind of what I'm trying to set the scene is, this is something that it's some particular issues are things that we should expect to be to happen at some point in time in the game of ultrasonics. So it's not for different suppliers or different exact products, but it's a general idea that I want to provide caution for, because it can surprise us, different aspects about the performance variation. Um, and yeah, what are my opinions based off of that I'm going to be talking today, regarding how you should specify your products. So they're based off of times that I've had as during employment for different ultrasonic companies, transducer companies, as well as different companies, different experts, veterans that I've had the opportunity to work with, as well as experience that I've had with many consulting through many clients. And some of these clients inherited products. Some of them are developing new products. They've worked with all sorts of vendors, and they've had different issues as well, depending on how far along they are in the process. So having issues with ceramics is not is a common thing to eventually happen. But it is definitely a solvable issue. But it's more bites you in the butt if you never expected that these products have the variation they may have at some point. So tolerances for piezo ceramic elements. So why do we care about that? So the PZT elements, and I'm just gonna say PZT because that's, I guess, 99.9% of the ultrasonic products in terms of volume, especially in terms of my clients. Everybody we're not doing single. I usually haven't had a single crystal client, but I've almost all the clients that I've had are using PCT ceramic elements, whether they be hard, or soft, sensor actuate, low frequency actuator type devices. So these elements produce and sense ultrasonic vibration, and being as you're watching this video or you're here live, you know that. So, but so what matters about that we really care about as the client of these vendors, as a company using piezo ceramic elements, is the performance of the final assembled ultrasonic transducer. So we potentially have influence over that, but there's some things that we don't have as much control over, which is some of the raw materials. You could say the ceramic elements being one of them. So we can specify, you can say whatever you want on a data sheet. It doesn't mean that it's cost effective for anyone to provide that, or they're willing to provide those exact specifications. So in this case, we're sort of in some ways left to also be aware that we may not, we'd like to have the ceramic variability be plus or minus 5%, so we can work on the rest of the stuff and get our variation to be low. Although that's not a realistic approach, just to dump all of your variability requirements onto the ceramics, which they're not responsible for all the variation either. So the assembly process and the device itself and the application. So not to mention the application, and other aspects of that application, which can cause variability. But it makes a lot of sense that you'd like to reduce, or you'd like to have a lower variability in your crystals, in order to build a lower variability final device. So I believe that the purpose of providing specifications to the vendor is not so they build to spec. We don't provide values so they will take these values and make ceramics according to that specific specification. Like I want a D33 of 300, so they're gonna build to the spec of D33 of 300. That's not how it works. And I'll explain how I believe it works. And obviously the best place to go to get the information is the ceramic vendor themselves. If they have a different process than I have been exposed to, then you're obviously they're best qualified to speak about their own abilities. But generally, there are certain ceramic offerings they have with different general material properties, and what you receive is representative of that class of materials, that composition, that processing recipe they have, but it's not particularly built to your spec unless you have a very unique application, and perhaps it's very interesting for them to do that work for you, which I have not seen, unless maybe you're a really high volume customer of theirs. So I'll explain more about that soon. So what can be specified? And this is the slide before I get into some of the advertisement for my company and my sponsor. So what can be specified? The electrical properties can be specified, and the mechanical properties can be specified on a data sheet, or on like basically a CAD drawing or specification sheet that you give to your manufacturer. So that's the resonance frequency, the anti-resonance frequency, and the bandwidth between that, or you can say the coupling factor, the impedance or the quality factor, and capacitance and dielectric loss. This pretty much sums up what you'd be able to put on a data sheet. You could have more internal requirements, but those are going to be the things that would be kind of across the board relevant. You can also put the obviously mechanical tolerances, dimensional tolerances, like how thick something is and how and the tolerances of that. That's pretty standard, I think. But the concentricity, flatness, and parallelism, these in many applications do have a huge impact on the final performance. But it's hard to know exactly what's too much. But these are things that you need to keep in mind, and it doesn't hurt to specify them in a general sense. Even if you're not sure exactly what they should be, you can kind of go off your what the vendor, what their standards are. that would be a good starting point, and also to be measuring them as well. So kind of being part of the quality control process of your of the ceramics you receive is very important. It's a you know you're just as responsible as the vendor for the quality of ceramics that you receive, in the sense that you know what you're getting and what parameter is critical, and how to maybe build a device including electrical and mechanical systems such that you can achieve the performance you desire. And now for the short advertisement period of the webinar. The sponsor for this webinar is PI Technology, PI Ceramic. They're a piezo manufacturer based out of Germany, but also having different global representatives, including in the United States. They have many of the different, all the different PZT formulations, and also they have lead-free materials. They also do, especially they're pretty famous in the piezo stack, piezo multi-layer devices, actuators, and they do have a huge amount of quality control. So that's one reason for, especially for applications where quality is a really high priority. I do recommend their products. And so you can contact them using, there's a link on my website, and there's also going to be a link in any information regarding this webinar too, like the comments or the description of the video, and through my emails. So I myself am run my company, Ultrasonic Advisor. So I provide consulting for companies developing ultrasonic transducers. I provide a whole different a lot of different services, from just consulting calls to practical hands-on work, ranging from circuits to finite element simulations, to data analysis and training. So I cover a lot of different areas that will really help get a company going effectively and efficiently in this specific field. So I worked on a whole bunch of different types of devices, including bolt clamp transducers. Again, I do simulations. I worked on sensors, microfluidic devices. What else do we have? Yeah, and just different medical devices as well. So I would be glad to serve your company if you have a need. So the best way to get in touch is through email or booking a discovery call on my website, and there are links for that around. Okay, so getting back into the topic. This is my methodology, generally my way of thinking about specifications. So I believe that after building good prototypes, and I'll get into more the step before this, the point is to establish specifications loosely, because these specifications are not going to be particularly useful in holding your vendor accountable for variation. Rather, it just kind of establishes appropriate norms for what one should expect, and the vendor themselves expects will be what they provide. So we establish specifications based on element measurements, not material properties. What this means is that if you get a disc, you don't specify like the compliance, or you can't specify the D33 because there are some measurement devices that go particularly for that. But you don't specify the frequency constant, really. You specify the element property, like the coupling factor, rather than other parameters. So we focus more on the measurements that we can do directly on the element, not material properties themselves. The intent of the specifications are to ensure that the ceramics meet basic performance requirements. It's not to, hold a ceramic vendor accountable, because if their process truly does change, there's little that you can do about it, and it likely will change within reason, or they would themselves kind of do use a large process correction and kind of root cause analysis in their office. It's not going to be that there's going to be a 10% shift in performance, and it may not probably ring an alarm for kind of revising their process according to the raw materials and the processing equipment they have at that point. So the intent of specifications, again, is not to make the vendor stay on their toes to meet the specifications. It's not something that you can just sharpen a tool and now it's the D33 value is suddenly back in spec. It's not like that. There's no calibration knob on these piezo elements, although there may be on the furnace and other aspects, but doing that kind of tuning is costly and not really worth it, and I think it's not reasonable to expect a vendor to work toward that level, because it's not practical or sustainable. So processes for manufacturing PCT elements, and I know I feel like in this presentation I'm giving a lot of like gloom about this whole scenario, but it's just that you stay aware. Like so many devices work on PCT elements despite the issues I'm mentioning. Many devices have already built inside of them calibration, device calibration, or the variation is controlled in different ways by the user and things. So it's not an issue, but if you're not aware that this can be an issue, it could cost a lot of money and time and headache, and you may be caught by surprise by something that someone like me or has seen many times over, and is not surprised by it. So variation can over lots can be up to plus or minus 20%. And that seems pretty extreme, because like on the could the value be 80 and then on the one side be 120 and another lot? Probably not, but probably, let's say if you're getting a value of 100, let's say it's for the D31, then it might decrease by 10%, or so it might decrease by 10%. But likely it's not going to decrease by 10% one lot, and then it's going to increase by 20% in the next. So, but this can be what you might expect, that these could be the range of variation that may occur over time, and maybe you'll get a specific value for several lots, and then suddenly things will change for various reasons in the processing, the raw materials, and the equipment. So here's the first step, is that you need to get samples from your vendor. You don't necessarily say, I want D33 like this, I want Q like this, but you do say you want frequency. So frequency is a common one that we do specify, and the vendors do have knowledge based on their materials about what size will get you that frequency, especially if they're common devices like 2 megahertz, ceramic elements. They typically have a very good handle on frequency. So that's pretty true. So after you understand what kind of application you have, you choose your ceramics appropriately, actuator or a high power or sensor, and then you need to estimate the geometry of the ceramic required, and the vendor should be able to help you to determine that. If the ceramic element itself is what's going to be the primary aspect of your device. If you have something with a horn or bolts and things like that, then you're going to need the finite element analysis to help you determine what size is required, and you're most likely going to change the rest of your the metallic components or the other components to hit the frequency and performance, rather than changing the ceramic or rehauling the ceramic size. So you have your first samples and you measure. You measure the piezo chips, elements. I was thinking what keyword to use in my title, but I guess I just settled on elements for the title. But so you measure them, you understand what the actual properties are, and this is impedance and impedance measurements, mechanical measurements as well. That being said, I'm not explaining how to do those in this presentation. I've explained it in many other ones about how to measure what we have in slide 6, which is around slide 13, resonance frequency and these parameters. I didn't really go over mechanical tolerances. Those are more well known, and probably people can have best practices on these type of measurements. Definitely more than probably I could speak about them for sure. And the mechanical, obviously, many times that's already in-house expertise there. But electrical measurements can be tricky because the sample holder you know, what if you have a spurious mode, like your resonance is not very well defined? What do you do in those cases? I'll explain a little bit on that later, but it's sometimes helpful to have an expert like myself help you assess what will help you understand if your ceramic elements have strongly deviated from an acceptable level of quality or performance. After you have those ceramics, you've measured them first, then you make working prototypes. Because if you build them first into the prototypes and they work, and then you undo the you either they're glued together, or if you untorque them, then they're going to be different. They may be different properties based on your assembly process may have changed. Their internal properties because their microstructure is, you could say, alive. The piezoelectric ferroelectric material microstructure is alive. It changes based off of stress and electric field. So you may have changed it. So measure before, basically. And if your prototypes are working, that's awesome. So now you have specs. Now you have measurements of the piezos that went into your prototypes that work. The next step would be to create a CAD drawing. So you not like informally send the tolerances through email, but have a CAD drawing with geometrical tolerances and performance specifications. And there's no benefit to over specification, like because you will get variation, but it's more to it's more to just to ensure a basic level of quality. And it will also take many lots for them to determine the process tolerances on your particular order. So if they will just commit to a tolerance level without producing many lots of your specific ceramic, then I think that's not a good sign that you will be guaranteed that material. You may ask them what they do if there is variation, what variation would signal a red flag to them. How you can ask those questions to your particular vendor that you're going with, and you may think three to four standard deviations depending on your sample size, and that's a statistical analysis. So you will receive plus or minus maybe 3%, 3 to 4 standard deviations from lot to lot. Probably within a lot you'll be within 2 or 3. So when you're doing tolerances, you think in terms of finding defects rather than simply controlling variation. And some aspects like geometrical dimensions you can control much more closely, and also frequency, but the coupling factor sometimes and the charge coefficient does vary, and also capacitance significantly can vary. But these parameters are all related. So typically when your capacitance increases, typically the coupling factor is conserved. And if you know what the coupling factor consists of, basically if you have a higher charge coefficient, generally your capacitance will increase, which will kind of not allow your coupling factor to change too much. So it kind of conserves itself. So having even if you just specified capacitance, it may actually just be sufficient, because based off of the whole process, if you just specify capacitance, they're not just going to send you a capacitor with that value. But if they actually still make the process the same, all those parameters track. Like D33 will track with capacitance, and that will generally just allow you to be that almost might be sufficient. But we can still add more parameters legitimately, so we do. But realize that one parameter always usually scales with other ones. So here we can give examples of some tolerances. I don't have particular value, so I didn't do the I didn't do the bad practice of going to my clients sheet, CAD drawings, and like say, okay, they put these tolerances on different products, so I'm going to just recommend those right now. So I didn't do that, but I will say that you can ask your ceramic vendor for general tolerances, and those are good that you should put on your drawing based on the standard practice. Also, based on obviously your fit of your assembly, like if you need a part to be, it can't be smaller than a certain size, then you'd obviously put that on there. And also measurements from the ceramics from the prototypes that you get, because there are instances where parallelism, and I mentioned this in slide 3, so we're on slide 15, actually slide 6. So parallelism, flatness, and concentricity these can make or break your device. So if you don't have if you don't have flatness in your preloading, you're gonna crack your ceramic, and concentricity as well, and parallelism. So understanding these aspects, and how critical they are and what you are receiving, if you continue to receive that, is important. And many of these things can be automated, imaging and things like that. So it's worth the trouble, I would say. I also want to put one another note here. So the electrode is also something that's specified as to what electrode pattern you want on your ceramic. And just note one thing is that sometimes we do leave the inner ID and the outer OD slightly unelectroded in order to improve electrical isolation or insulation from arcing or sparking. So that can be something that you include in your specification, or you can ask for the entire surface electroded. So here's the electrical tolerances that I recommend having. So capacitance and dielectric loss. Why I like these parameters so much is because it doesn't matter usually the LCR meter, as long as it's an LCR meter, not like a oscilloscope or analog discovery or thing like that. If it's a dedicated LCR meter, it will do it despite the sample holder, because this is a huge issue with measuring resonance of piezo elements, especially for small elements. Despite the sample holder, it will most of the time you will get very good, very repeatable measurements for capacitance and dielectric loss. So dielectric loss actually is related to the quality factor, and capacitance is very closely related to the charge coefficient. So in a way, you're getting really reliable measurements, slightly indirectly, because it's not the exact piezo components, but you are able to get a good handle on the dielectric loss and the capacitance. So if there are issues in measurement elsewhere, in the other resonant impedance measurements, you'll suffer less. So capacitance can vary a significant amount. Either you could put a tolerance of plus or minus 20% from a few small batches that you got for your prototypes, or you can ask the manufacturer what they put. If they recommend a tolerance, like if they're fine with a tolerance closer, then I would always then obviously assume that that would be the best option. However, note for strict industries like medical devices and things like that, if you over tolerance your device, your ceramics, and then you receive ceramics that don't work well, that fall out of that, but still have good quality, then you will not be able to use them, and there'll be a huge activity as to justifying that they still work and why. So you need to be careful as well and be realistic, because this plus or minus 5% kind of is a common idea amongst engineers, like especially in measurement and other types of areas. But it doesn't work so well if you still, even if you have a large variation. Sometimes that variation is controlled by your user. I know from definitely surgical and things like that, you're watching, and as you're watching the tool as it works, or for welding, let's say, there's active calibration going on. So yeah, that's something to note there. And here for the resonant frequency, and I'll just highlight these. Resonant frequency, it depends on the geometry and material properties, but it's very, very related to the geometry. It's something that manufacturers really watch closely. So either you could do plus or minus 5% or probably closer. I would get with the manufacturer for what they will allow and what your application will be fine with as well. Because you may specify a tolerance, but you haven't received elements of that outside tolerance. So suddenly your device is a fixed 2 megahertz, but you get slightly off. Now your device works a lot differently. Some devices still may work, some may not. So it's something that you have to take ownership of, be aware of, and even maybe save those crystals and materials that are not in your normal specification range, to see what happens when you do put the other crystals in. Like if you're using PZT-8, you might choose to order some PZT-4 crystals just to see if how different material variation, how that affect your device, and what you could do to be more flexible in your final device, given that your ceramic, you don't have as much control over your ceramic elements. Be careful about specifying resonant frequency with spurious modes, like a thickness resonance, especially if it's not a disc, if it's a square shape, you will not be able to measure it well. Often also with a disc shape, if you're doing the thickness resonant mode, you'll have sample holder interaction, and many other reasons for having spurious modes that make your device inconsistent in terms of the measurement of that property. So it's possible to specify other modes like the radial resonance, for example, for a ring, instead of the thickness mode. So because the radial and the thickness mode have related properties. So you can specify both, but maybe primarily, let's say, rely on the radial resonance in case the thickness is not appropriate. So you can, contact me if you have more questions and issues about, the measurement quality is not good because there's a spurious mode, and it's an interesting topic about what you could possibly do there. So the coupling factor can also be used, but I find it's easier to use the difference between the anti-resonance and resonant frequency. It helps to define the charge coefficient indirectly, because you could also specify, I don't know if I had the next slide, you could specify D33, and there are D33 meters, and they are variable in their measurements, and there's not a particular standard about them. So it's useful. It's an easy check about the charge coefficient. So I would say it's useful to specify a minimum value, but not look at it such as like a plus or minus value that you would look to first to understand if your properties are within range, but they should be above a certain value, and your manufacturer vendor can supply that information. All right. You can let me know if there are any questions. And I just want to end with some stories or things that can happen. Basically, I could probably change that. Things that can and probably will happen. And final thoughts. So these are things that, and this is not working with the Asian supplier or European or American piezo ceramic supplier. This can happen, and I have seen these events happen across all in this particular batch. I actually could say one is from Asian, one is from European, and one is from American. Actually, I can say that from these three examples I gave. I won't say which one is what, but I will just say that it can happen. But having a supplier dedicated to quality like PI Ceramic definitely can be a huge asset when working through issues that can come up, and so I'll definitely mention that. So in one case, the vendor switched the supplier of one of the powder components, and this significantly changed transducer performance. And this wasn't known to the specific customer of that vendor until they approached the vendor. So I think this is probably a case where there wasn't enough maybe specifications on the data sheet, or even maybe there's a 10% change, and that kind of was included, but it's like we don't really know what happens when the 10% a property changes by 10%, what other things go wild and crazy. So in another case, the transducer performed at 10% lower amplitude, and it was just found that the new lot from a vendor changed material properties for no reason, in particular from 10% from the mean of previous lots. So this could get you out of the tolerance range in some cases where you're kind of like varying. You specify a mean based off no knowledge at all, like what's going to be the mean. You may like, let's say you're getting ceramic values of 80 or let's say you got ceramic values of 100, between 100 and 90, you're usually getting between 100 and 90. But then you get another batch with a mean of 80, which is kind of like maybe it's even statistically possible, or maybe not statistically possible. But it's still kind of the mean values are only like 10%. If the mean was 90, then 180 would only be 10% different, approximately. So it's kind of, we're looking with foresight, not with hindsight. So in order to include and account for future variation, we have to propose more variation as possible than will actually happen based off of the mean, the possibility of the mean going both ways. Another case was that an R&D batch was different. Like a small batch of samples was ordered, and the new batch was 10% different and looked quite different in the measurements. It's also possible. So you know, for example, ordering a lot of material is a good practice. Being aware that these changes can happen and addressing them and asking your vendor earlier on. But when you're just very early on in a new product and you don't have transducer ceramics already, I mean, from that vendor, it may be useful to work with a consultant like myself who maybe has some rapport and can help guide you toward what's reasonable and get you maybe a bit more kind of presence and importance in these scenarios. But yeah, again, I recommend PI Ceramic as a you know, high quality vendor um, who would be a great partner to any company that that needs piezo ceramics, although there are also other vendors that produce good product. So the moral, vendors are committed to quality, but variation is inherent in the production of PZT because there is a defect chemistry which is used to manipulate the properties of the piezo ceramic. There's thermal processing furnaces with like 1,000 degrees. There's electrical processing, there's machining, there's raw components. If there's defect chemistry, then the raw components and their quality that they receive and the prices that you have for these ceramic elements also weigh into how much tuning is done, the size of the batches. One question is, hey, why don't I get a secondary vendor? I have not seen a company that uses a secondary vendor. I mean, I haven't worked with all companies, obviously, that do piezo ceramics, work with them, but I have not seen a transducer company using two vendors at the same time before. So I would not suggest, if you're getting into this field for the first time, you should not look into a secondary vendor. It's not standard practice to do. I have not seen it. And the kind of the long-standing companies, and also with newer companies developing ultrasonic transducers. But it seems like a attractive proposition, but it's simply not what happens in practice, because then you'd have to account for these things happening at two companies at once, which would be interesting. So also note that other materials have variability, but they don't have as many like properties that you're concerned about. Like especially material like titanium can have significant variability based off of many things, including your vendor of titanium for the same brand, for the same like composition or specification for different sizes that or different bulk material geometries that you may get, like different rod stock, whatever you machine it out of initially, how that is manufactured, all those, even if it's the same composition material, especially titanium has a lot of variability. So it's not just piezo ceramics, but here with piezo ceramics, we're super dialed in on the variability because we can measure very easily, because you have electrical measurements that you can even get mechanical info like resonant frequency out of. But for things like titanium, you can make a rod stock and like, you know, hit one end and measure the frequencies and stuff and such, but really you don't get it like that. You basically get the horn and you don't measure the frequency of the horn by itself most typically. So we're not as exposed to material variation and other properties, but in no way should we think that PZT is like a unique thing in the whole world, that nothing else has variability. Especially titanium in the ultrasonic world may have a lot of variability. That But because it's just mechanical in nature, it's less than the electromechanical elements of PZT, which has many different processes which go through it, and they're also produced at different levels of volume than PZT is. So in summary, so formal PZT specifications are developed, in my opinion, via hindsight, and implementing loose tolerances. So the goal is to detect defects, not just variation control. There's other methods of variation control, from like pairing ceramics. If you use multiple ceramics in one device, you pair a low value with the high value, and suddenly you arrive at a middle version. Or you have electrical controls that can adjust for that performance difference. The mean performance shifts between lots is a huge challenge. That can appear suddenly, and it's to be potentially expected that this will eventually happen. Customers, and I've seen it happen in multiple instances, so but I can't speak for all piezo, all ceramic users everywhere, anywhere. I can't, and every device, I can't speak for that, especially probably really high volume elements. There's likely much more control and even dedication of the vendor to provide consistent product, because they have the means, they have the volume to tune processes, to understand where variations coming from, and to hone in on their process. So customers typically need to have strategies in place to account for in-lot and between-lot variation, especially for low volume customers. Also, understand that the sample holder effects can really affect your measurements, which is why I'm a really big fan of capacitance, because it doesn't have many sample holder effects, but the differences in equipment between you and your manufacturer may disagree on the exact measurement values. So that's a challenge to navigate, but it is definitely possible to get through, and having a good data sheet for an appropriate stage of your product is important, so you understand what you need to. It's not only just for the supplier, it's also to understand when you receive devices that they may be out of specification, and what that does, and can you indeed expand your range, and to know that you have a particular performance differences for a particular reason. Measurements of your ceramic elements is important before assembling your device. So I'll stop the recording, and I'll ask if there are any questions here. So let me stop.